We are going to start with a review of the laws of the exponents. I think we went over this earlier because we needed it. Now here it is in the book, so we're going to go over this pretty quickly. This is section 5-1. And the reason is we're going to be manipulating polynomials. Polynomials have exponents, and we need to know how to work with exponents. So the first law is that you have a to the n times a to the m. That's equal to a to the n plus m. Well, what does that say? That's something like 3 squared times 3 to the 5th. Well, this is just 3 times 3, 2 times, right? This is 3 times 3 times 3, 5 times, and instead of, going through all this, you can just add the exponents. Right? That's all this means. It works even if n and m are negative. You don't have to go through any kind of gymnastics in that case. This is multiplication when we're dividing. You multiply, you add the exponents. When you divide, you subtract. Just when you're adding, it doesn't matter how you add. But when you subtract, remember the one on top, you subtract the one on the bottom from. And again, this works just fine whether a and m are positive or negative, or 0 for that matter. There's a catch. For this, a is not 0, of course. A were 0, you'd have a 0 in the denominator, and we can't do that, of course. Here's kind of, to get to the next rule, I'm going to actually use that, what I just said. If I let n equal 0, m can just equal m. That would be a to the 0 over a to the m equals a to the 0 minus m. Well, assuming a isn't 0, who can tell me what a to the 0 is? Raise your hand.
1.
It's 1. It's always 1. So if I rewrite this, I get 1 over a to the m equals a to the 0 minus m is just minus m. So that's, except I'm going to rewrite it with n's. That's my next law. 1 over a to the n equals a to the minus n. And again, keep in mind that this doesn't mean that minus n is a negative number, that n is a positive number. If I were to do this, if I was to say, well, what's 1 over x to the minus 3? Well, using this formula, that would be x to the minus 3, but I think we all know minus of a minus. Negative of a negative is a positive, right? So this is just x cubed. Again, another little pearl of wisdom is you can move factors with exponents up and down, you know, over the dividing line by just switching the sign on the exponent. Okay. I'm gonna use a room over here. The next law we want to remember is a to the n raised to the m. And just let's be clear about what this means. If I said, like, here's a number, 5 squared raised to 3. Well, this is 5 times 5 in here. To the 3, well, I have to repeat this 3 times. 5 times 5, 5 times 5, 5 times 5. Well, that's obviously 6 5s. And that gives us this formula, A M, A N M, doesn't matter. So when you have something raised to an exponent and you raise it to another exponent, you just multiply the numbers. Let me just show you a trick where you can use that in reverse. Let's say I have the square root of x and to the 6th. Okay. Well, I can rewrite that as square root of x squared to the 3rd, because 2 times 3 is 6. And I know that the square root of x squared is just x. So this would just be x to the 3rd. There's other ways to handle this. Maybe we'll get to that in a second. This is nice and convenient. Okay. So let me transfer this rule over here. A to the n to the m equals a to the n. M comment. Again, n and m, it could be positive or negative. It still works. They can be fractions. It still works. Just a general rule. Okay. A lot of these. We're only halfway through. Okay, the next rule, you have a and b, and you raise that to some power. So if I had like 3 times 5 and I raised it to the 4th power, well, that's 3 times 5, 3 times 5, 3 times 5, 3 times 5, which I can rearrange. 3 times 3 times 3 times 3 times 5 times 5 times 5 times 5 is 3 to the 4th times 5 to the 4th. That is, this 4 can distribute across here. Now, I don't remember exactly, but I think the last time we went through this, there was a little confusion. We had something like this, 3x squared. This is a variable, this is a constant, but we treat them the same. here, we have to distribute the 2 over each of these. So this is 3 squared times x squared, which of course is 9x squared. So just something to keep in mind. These are, doesn't matter whether there's a variable, a constant, or we actually have a number. Something you want to be very careful about. If I write -5 squared, the problem here is the book, I think that your book and I do not agree. Your big book thinks that this means this. I think it means this. There's a big difference here, right? This is -25. This is -5 times -5 is positive 25. So whenever you see something like this, be very careful. See it on a test and you're not sure what I meant, you can ask. If you want to make it perfectly clear to me what you mean, you could always put parentheses. Reason I mention this is if I wrote like -2x squared, well, this is because there's a parenthesis here, it's perfectly clear. This is -2 squared times x squared. Well, the negative goes away. It's just 4x squared. So you do want to be careful when you're using exponents and you're mixing them with negative signs. Okay. Here we have, we're multiplying 2 factors and raising them. This really isn't very different. If I have a fraction and I raise it to a power, that's the same as raising the numerator to the power divided by the denominator to the power. Okay. We're almost done here. If I expand on this a little, instead of a over b to the n, it's to the minus n. Well, surely I can use this rule and I say a to the minus n over b to the minus n. But then I can use this rule which says if I move something up or down, it changes the sign. So I can move the a down and make it positive n. And I can move the b up, becomes positive n. And then again, by this rule, it becomes b over a to the n. So I think that needs a real example. So if I said 3/2 to the minus 3. Well, you could say, well, that's 3 times 3 times 3. Oh, wait. 3 to the minus 3, 2 to the minus 3. Well, that's 3 over 3, 2 to the 3. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. Okay, I got it the hard way. But according to this rule, I could just say, oh, that's 2/3 cubed, and then go directly to here. So this can be useful. I have another rule here, but I kind of wrote it already. Just take this piece, let's move it down here, a to the minus n, b to the minus n. This just, oh, you know what? It's not the same rule, I'm sorry. Forget what I said, it's a different rule. Kind of almost the same. I have a to the minus n over b to the minus m. Well, again, I just move the b up and change this to a positive, and I can move the a down and make the n positive. All right, those are it's a bunch of rules. Some of them I think you probably know pretty well, hopefully, and a few of them I think the most important ones right here, here, and here. The other ones you can probably figure out as you go along. Let's do some examples. Let's try some examples. You have some paper handy. So I'll go over here. All right. Now, the goal here is to simplify. When being asked to simplify, sometimes there's some ambiguity. What is this simpler than that? But in these, I think it's pretty clear. So the first one is just x squared y to the fourth times 3x. So go ahead and simplify that. All right, anyone want to render an answer? Harder than I thought. Now, what I would like is if someone's confused, I'd like them to raise their hand and say, this is why I'm confused. Because if you're confused, that means I didn't explain something well. And probably other people need me to explain it. If you're sleepy, just put your head down on the desk now when you're asleep. Nobody? Who's going to tell me that? Oh. Is it easier if I do that? Yes, Kate?
How is this right place? It just 3x to the third y to the fourth.
I don't know why you're not sure, but
I don't know, it seems like so simple.
yeah, it's just, yeah, I've seen that happen. Something so simple that it's like, okay, all right, that's exactly right. Don't, you know, it's going to go the other way. Something's going to seem too hard, and it's going to scare people too. All right, let's just jump right in here. X to the n, y to the 3n, or x squared, y to the 4th. How about that? And just as a general hint, if you can get rid of the division line, that's usually simpler. So you've got exponents at the top and the bottom. If you can move them all to the top, that's usually a good thing, even if you end up with a negative. Someone have an answer for me?
I don't know mine's right. I said x and n minus 2, and then y 3n minus 4.
All right, class, you're batting 2 for 2. Very good. That's all there is to it. One last one. Okay, anyone? Anyone want to take this tab? Yes?
Would it just be negative 2y 10?
How did you get 10?
Oh, sorry, I thought that was a 5, so it's 6. 3 times 2 is 6. Sorry.
My apologies for my awful drill. Anybody get anything different? Hope not. Okay. All right. Laws of exponents will be, I think, I don't know if it's posted yet. If not, it'll be soon. Homework assignment just to get a little practice so we, have some gymnastics. Math gymnastics, I guess. Because we're going to need this throughout the class. Oh man, there's something wrong with this board. It doesn't erase properly. Erase. You know why the last person left the board kind of a mess. Okay. Okay. The next couple minutes are going to be a little like a vocabulary lesson. We're going to look at polynomials, which is section 5-2. Now, first question is, any Latin majors here? Anyone taking Latin? I don't think you need to know Latin to know this. What does poly mean? This means many. So, it means many, it must mean many nomials. What's a nomial? Well, we don't really have a nomial. We do have what we call a monomial. A monomial is an expression that looks like ax to the n. Now, n could be 1, so we won't write it. Could even be 0, in which case this is 1 and we have a. X is a variable, some number we're going to plug in, and a is just, it's a number we kind of think we know. It's what we call a constant. Okay, the number n, the exponent in a monomial, is what we call the degree of the monomial. And if this is a monomial, a polynomial can look like this. Now, here I'm just using an n down here as a subscript. That doesn't, it's just, I have a bunch or a list of a's and I'm labeling them. This one I'm labeling a to the n. But I use the n here to mean an exponent. So there's a monomial. Here's another, but we'll get to what this is. This one. Okay, so this is what a polynomial looks like. It's a bunch of constants, these a's, which I'm labeling them nice and conveniently, matching them up with the degree or the exponent on the x. Now, I said there's a lot of vocabulary here. Each of these monomials, including this is just some number, we give the additional name a term. Terms are the things we add up to get the monomial. This term, the one at the end, we call the constant term because no matter what x is, it's not going to change. Now, as I mentioned, here the degree of a monomial is just that n. For a polynomial, the degree is here, it's the largest n. So, for example, you're probably used to seeing an expression like this. What's the degree of this expression? this polynomial. Yes? It's 2. Just look here. The largest exponent on x is 2. This is degree 2. I might add, we categorize polynomials by their degree. The smaller the degree, the easier they are to handle, easier they are to solve. You know, the larger, the more complicated solving an equation would be. Okay. We're already, I think you're already pretty familiar with something like this. This is a polynomial, what's its degree? 1. And we have a special name for polynomials of degree 1. They're called linear. Now, of course, that word linear here has to do with the fact that if we graph this, we get a line, right? But things that are linear in math, we run into this a lot, and actually a lot more to it than it just being a line. But that's the term we use. That's the vocabulary word we use. Does anyone know what we call, as a general term, for polynomials of degree 2? It's a general term you might have run into. Actually, I know you run into it. Hint, there's a formula into in the past. We're not learning this right now, I'm just throwing it up here.
Is that the quadratic equation?
That's the quadratic formula. Polynomials of degree 2 are called quadratics. It's an equation called a quadratic equation. And if it's a quadratic equation, we'll get to this later in the class, the quadratic formula. Okay. So sometimes when we're talking about polynomials in general, we're not being specific, we'll sometimes write something like this: P of x. Like we mean some polynomial, but we're not being specific. And if we said P of x equals 0, we've got an equation, we've got a polynomial equation. So one of the things we're going to do in the class is we're going to learn how to solve polynomial equations. We already know how to solve linear polynomial equations. Some of you may remember some of the ways that we have a few different ways of solving quadratic. Oh, here's just a little history. This is linear. This is quadratic. Wait a minute. Quad. What's that root mean? What does quad mean? Yeah, it means 4. What's going on? Why is this 2 of 4? And there's a history lesson here. But it goes back to the Greeks. The Greeks didn't have algebra. Algebra kind of came out of the Middle East. I don't know, I'm guessing now, around 1300. I was reading recently, they were saying, no, it actually, they got it from China. I don't know. Algebra came through from that period. The Greeks, before then, could solve some of these equations, but they couldn't use algebra. They used geometry. And there's a way using a rectangle, kind of like this. This is squared. X, 2, 4, or something. They're using a rectangle. A rectangle has 4 sides, thus the name quadratic stuck. It's a little more obvious when we get to 3. It's called a cubic equation. Cubes kind of have, well, they have 3 dimensions. All right, unimportant detail, except, don't be confused. A quadratic does not have degree 4, it has degree 2. All right. Okay, so there's some things we need to learn how to do with polynomials. I guess we can go over here. First thing is we want to know how to add 2 polynomials. So, for example, 2x squared plus 4x minus 1. That's one polynomial. We're going to add that to x squared minus 3. You may have run into this before. It's pretty straightforward. What we want to do is combine like terms. Remember that vocabulary? We're talking about terms. So what are the like terms here? Well, 2x squared and x squared are like terms. So let's put those 2 together. Well, 4x is just all by itself. And then we have minus 1 and minus 3 there. They're also like terms. Now, this is pretty clear, 2x squared plus x squared. But one way to think of this is using the distributive law. We say this is x squared times 2 plus 1, right? Using the distributive law backwards, where we're factoring the x squared out. And so clearly this becomes 3x squared. We just have our 4x term, and minus 3, minus 1, minus 4. That's how we add polynomials. Now, as an alternative to the way I wrote this, you can think about the way you do normal adding of long numbers, right? Which is, you put one on top of the other, and you align the like terms. And then it's just kind of like regular addition. You just be careful that you're adding, apples and oranges, x squares, and numbers without x's. So here we have minus 1, minus 3, minus 4, 4x. Well, this was kind of 0. And here we have 3x squared. Now, I mention this because, again, when we go to subtracting polynomials, you have a choice, and whatever you feel most comfortable with is what you should do. So let's look at an example. Okay. So my example here is pretty simple. 2x squared plus 4x plus 3 And then I want to subtract, and I'm going to put parentheses here so I don't make a mistake. 3x squared minus 2x plus 1. Now, if you're going to do it this way, I suggest you distribute this minus, right? This becomes a plus, this becomes a minus. Since it was already a minus, it becomes a plus, and it becomes a minus. And now I just have an addition problem, right? Just like with regular numbers, subtracting a negative is adding a positive. I'm sorry. Subtracting a positive is adding a negative. Yeah, that works too. So that's, but again, adding, I'm going to combine the like terms and so forth. But, go back. I forget what that was. Doesn't matter. You can also line them up. Just be careful. Well, 3 minus 1 is easy. 4 minus 2. This is usually what trips people up. Simple mistake. It's not 4 minus 2x. It's 4 minus 2x. Well, that's 4 plus 2x, right? And here, 2 minus 3, we end up with minus 1x squared. I guess that was the easier part of manipulating polynomials. We're not going to get that far today, are we? All right. There are really two situations you're going to run into. And who here has not heard of FOIL? I guess that means everyone has heard about FOIL. First, outer, inner, last. Now, FOIL only works if you're dealing with two polynomials that have two terms. Most commonly, they're linear. The way this works is, you just follow the leader. First, these are the firsts. X times x is x squared. Outer, x times minus 2. Inner, 3 times x. And last, I'm not going to draw it, minus 2 times 3 minus 6. And then, I have to combine these. You don't actually have to take an extra step. When you do the inner and outer, you can just say, well, 3x and minus 2x, that's just x. So FOIL is a simplified version of multiplying polynomials. It's really common. Now, it works even if these aren't linear. For example, if I wanted to multiply x squared plus 1 times x minus 2, I can still use FOIL. I just have to be careful about my exponents. Here my firsts are x cubed. My outer is minus 2x squared The inner is plus x, and my last is minus 2. So that's the simplification of FOIL. Did you have a question? No, okay. But unfortunately, we're not always so blessed that we're just dealing with one of these, you know, two-term polynomials. So when we start with something more complicated, we have 3 terms. And let's say, just say x plus 5. It's best to do it like long multiplication. Right? That's what we did before we had calculators, long multiplication. We start over in the ones column, except this is just the constant terms. So 5 times 2 is 10. 5 times negative x is negative 5x. You want to be careful, give yourself a lot of room. Do this carefully so you don't make a mistake. 5 times 3x squared, that's 15x squared. You want to watch your pluses and minus signs here. Right? X times 2 is 2x. X times minus x is minus x squared. And x times 3x squared is 3x cubed. And then just like with long multiplication, we're adding the columns. There's no carrying. This is nice. Minus 5 and 2 is going to be 3x. 15 and minus 1 is 14x squared. And we can just bring this in. Okay. That's multiplying. It says subtracting, but you know, it's multiplying a polynomial.
Is it 3x a negative or a plus? The other one?
Well, it's plus here.
No, the negative x, 2x. Is that negative?
Oh! You see? You got an option. Absolutely. Oh, wow, I got that one. Or if you prefer plus negative. So obviously we're going to stop here. Just to summarize, so we have this new monster called polynomial. Just hold on a second, relax. We'll get out in 60 seconds, guaranteed. We have a bunch of vocabulary associated with it, so we can talk about it. We know how to add them, subtract them, multiply them. We're not going to worry about dividing them at the moment. And we'll pick up there on next Tuesday. Okay, thank you.
Thank you.